Okay, I am recording, and so I will hand the floor over to Group 7 to share with us your bioincubator design.
Awesome. Well, good afternoon, everyone. Thank you so much for coming. As Dr. Trump said, this is Group 7, and today we're going to be presenting our incubator final concept for Mech Design 2. This presentation is going to cover our Hedgehog concept, a product overview, and an in-depth look at each subsystem's key concepts and attributes. We'll also be providing cost breakdowns and comparisons with the competition. Next slide, please. Our Hedgehog concept was to design a bioreactor with the fewest parts among the competition in order to ensure accessibility and implementation in a wide variety of lab environments. An auxiliary benefit of this goal is significant cost reduction for both materials and assembly. Next slide, please. The small text here, but the primary design intent was to create a reactor which can dispense liquid and gas in both well plates and test tubes, monitor the various statistics within those environments, and ensure mixing and maintenance of each environment. Each team member was responsible for the development of one subsystem, which were integrated using a down selection process to produce a ready for prototype concept. We're confident that our concept can meet and exceed the Biofoundry customer needs, and we are very excited to share it with you today. Next slide. So the first consideration was the frame. We had some human factors requirements according to the customer needs statement that we had to meet, and this was where we decided to meet those with a single unit design that was simple and compact and could house the entire assembly. The physical stability and the insulation were two of our big design challenges. How we could insulate it to prevent heat loss, and how we could ensure that it could function in a lab environment without toppling over accidentally. Next slide, please. The technology readiness level for this system is level 6 because 80-20 extrusion is typically just used in a laboratory environment. Should this design move past the prototype stage, we would definitely use a purpose-built rigid frame to further simplify our design and reduce the part count. Next slide, please. We determined that there would be 7 customer needs that would be addressed by the frame itself. The first 2 refer to the physical size and weight. Need 4 is really our bread and butter because it calls to minimize the number of parts, which were coming in at 172 parts, all included for the frame. The 80-20 frame exceeds the required factor of safety, and we calculated that it would not tip over due to an accidental bump during lab use by calculating where the center of gravity would be. Coating the aluminum using physical vapor deposition would prevent corrosion and prevent reactants with specimens or other chemicals that might spill on it or otherwise come into contact with it. And assembly itself is BSL2 compliant because it has a closing and locking front door, and it employs a mechanism for collection and neutralization of waste. Next slide, please. Some of the key features that we have in this in the frame are cavities to ensure insulation. We'll probably use a polystyrene foam to insulate in between those cavities. It's sort of sandwiched in between the sheet metal, if you can see on that cutaway. The front door is made of borosilicate glass, which is essentially just Pyrex, in order to be able to view the specimens and also being heat and chemical resistant itself. Also, we have spars inside the walls to mount various apparatus, which we'll get to in the next couple slides. Next slide.
For our liquid dispensing mechanism, the purpose was to transfer fluid from a storage unit to a needle on the dispensing unit via tubes. The process that we decided to go with was to use a periphalistic pump in order to conduct two-way fluid flow from either the storage unit to the needle or from the needle to the waste mechanism. Our TRL for the liquid dispensing mechanism is a level 6 because the media bottles that we decided to use have been used in lab environments before. However, we have not specifically tested our exact scenario. And failure results in only fluid flow stoppage, so this is not a major concern. The customer needs that we have with the liquid dispensing mechanism vary from size to speed. This need 1 relies on the fact that the liquid dispensing mechanism has to be small enough to fit on a benchtop, and since it fits within the frame, this is already met. Needs 15 and 35 are pretty similar, where they have to deal with waste and reaction, where the waste needs to be able to be extracted, and there needs to be no reactive materials that can react with the fluid. This is done by using no materials that can react with the fluid, and also the peristolic pump allows for the reversal of fluid, so the fluid can be removed without having to take the entire device apart. Additionally, the fluid needs to be dispersed at a certain rate and a certain amount, and the peristolic pump allows for this to be sped up, slowed down, and also controlled. The key features we have of our liquid dispensing mechanism is using the peristolic pump allows for two-way flow for addition and subtraction. The peristolic pump also allows for the flow rate to be met and the exact volume. The duckbill caps we have included on the top of the media bottles allow for one directional flow either out or into the bottles, so that when waste is being put into the waste bottle, it cannot escape, and additionally, the fluid can also come out of the storage unit. The storage components we chose were the media bottles. This was for easy removal and sterilization of the bottles in a lab environment. Additionally, plastic tubing was used to connect the bottles from to the dispenser. And additionally, we have included needles at the base of the dispenser to allow for liquid dispensation through the rubber caps on the test tubes. So the gas and the fluid are able to go into the test tubes, but also not escape them.
We have designed a custom motion system that is fully autonomous and can follow a pre-programmed set of instructions. We were inspired by similar systems already present in devices such as 3D printers or laser tables. Our motion system sits above the culturing well plates and tubes and can freely move in a roughly 1 foot by 1 foot by 7 inch space, which allows it to access and process any tube or well within that area. This system is capable of moving very quickly, up to 2 to 3 meters per second. We calculated a minimum required speed of 8.5 millimeters per second, so we have easily exceeded that. Whether the user wants to fill an entire rack of tubes with gas and culture medium, or they just wish to extract waste from a few specific tubes, they would have that flexibility. The basic design of the system uses 2 motorized belt drive axes for X and Y motion, as you can see in the bottom left image, and a motorized linear stage for Z motion of the liquid and gas dispenser. The dispenser moves vertically to access the tubes and wells, or to move out of the way as the X and Y axes move the dispenser to the next tube. The whole system was designed to be light so that the motors would not be under significant stress, but also rigid so that the positioning of the dispenser has as little error as possible. The basic function of sequence is as follows. The user can create any number of command sequences using G code or a similar code, much like you might program a CNC mill. Once the program is created, the user simply needs to push a button and the system will begin moving the dispenser to its desired location. The dispenser will move down to pierce through the rubber caps and begin depositing liquid or gas. Alternatively, input can come from the optical density and fluorescent intensity sensors, which could trigger addition and removal of culture medium or gas without the need for user involvement. Next slide, please. There were a number of customer needs that were used to influence the design and down selection process. Our system was designed to be compact, but still achieve its function. And the motors used to power the belt-driven axes can run on a typical wall power source, and the Z-axis lead screw motor can be mated to an AC to DC converter. Costs were kept to less than $900, and the system is capable of operating on a wide range of temperatures. Next slide, please. We chose the belt drive technology since it offers a number of benefits. In addition to being much faster than, for example, a linear actuator, it also offers sub-millimeter accuracy and good repeatability. The belts do not require any lubrication, which is very important in the laboratory environment, as you do not need to introduce any potentially contaminating chemicals to the incubator, and it cuts down on maintenance needed. This simple 3-axis gantry system is easy to assemble and modify, if the user wishes to upgrade or add new functionalities. Next slide, please. The technology readiness level of this subsystem is a 3. Although the constituent parts are proven products, we have not been able to test how they might work together in our specific design. Many systems similar to this one exist as standalone products, so we feel that our design is very feasible, but we cannot confirm that through testing. However, the risk associated with this system is low, as failures would not be catastrophic. Next slide.
Okay, so the well and tube storage subsystem is responsible for holding and shaking the culture plates and for taking the optical density and fluorescent intensity measurements. The subsystem is comprised of a purchased incubator shaker, Arduino breadboards with LED lights and corresponding photodiodes for the OD and FI measurements, and a manufactured rack that is bolted onto the shaker to hold the culture plates. The tubes are sealed with rubber tops to allow for individual culture atmospheres. Next slide, please. The well and tube storage subsystem has a technology readiness level of 5. The LED and photodiode method of measuring optical density and fluorescent intensity are currently being used in the KaiBio and Evolver turbostats. The purchase shaker is used in incubated industrial settings to linearly and orbitally shake cultures. This system is TRL level 5 because even though some of the subsystem components are ready for industrial usage, the equipment is undergoing modifications and not all of the components have been used together before. Next slide, please. This subsystem addresses many of the customer needs. Customer need number 4 requested that the incubator be assembled and disassembled with minimal know-how and be easy to clean and service to mitigate contamination. This customer need has been revised to the metric number of parts because the fewer the parts, the fewer the steps the technician must undergo to assemble and disassemble the incubator. This concept had a total of 87 parts. The tubes are interchangeable and allow for the addition and subtraction of liquid and gases to maintain individual atmospheres for each culture via the rubber seals as per customer need 21. The incubator can also hold 3 well plates, 6 50 milliliter tubes, and 5 15 milliliter tubes at a given time to accommodate for the customer need 22 and 23. Next slide, please. Each tube has a 650 nanometer LED and photodiode to measure optical density and a 470 nanometer LED and photodiode to measure fluorescent intensity to accommodate for customer need 28. Customer need 30 requested that the incubator achieve a light intensity of 1 kilowatt per centimeter squared at 640 nanometers, and this light intensity requirement is addressed with the LEDs used to measure the optical density. Customer need 31 requested that the incubator have linear, orbital, and double orbital shaking patterns, and our selected shaker will be able to linearly and orbitally shake the tubes. Customer need 32 requested that the incubator have shaking patterns and atmospheric conditions that are independent for each tube. And this need was addressed with the implementation of the rubber caps as mentioned before for the independent tube atmospheres. However, the chosen design will not be able to individually shake each tube. Next slide, please. The photo to the left is a snapshot of the well and tube storage subsystem inside the incubator, and the photo to the right is the exploded view of this subsystem. The rack that will hold the wells at the top of the exploded view will be manufactured out of aluminum sheet metal and will be bolted to the purchase shaker. The rack has 2 rows of tubes that are sandwiched between breadboards that are fastened to the shaker. The breadboards have 650 and 470 nanometer LEDs on one side and the photodiodes on the other. The LEDs will shine light through the width of the test tube, and the photodiode will read how much light is transmitted through or emitted by the cultures. The photodiode measurements will be translated into optical density and fluorescent intensity readings. Next slide.
Okay, so for the gas regulation and injection subsystem, the controller is able to inject precise quantities of nitrogen, oxygen, CO2, methane, and hydrogen gas into each rubber-capped test tube, which provides completely automated closed-loop control of atmospheric conditions for each tube. And the design uses 4 on and off solenoid valves and 1 motorized ball valve for controlling the flow rate of each gas. And because this gas injection needle is attached to the dispensing arm of the motion system, The controller can regulate the atmospheric conditions within each rubber capped tube individually. And this design is capable of pumping out effluent gas as well as residual gas left over in the hoses to ensure precision in regulating controlled amounts of gas for culturing cells. Next slide, please. So the technology readiness level for this subsystem is a 4, as the off-the-shelf pneumatic components, such as the valves and fittings, have been tested in a lab for conditions such as maximum allowable pressure. However, these components can be used for a variety of industrial applications, and the operation for injecting and capturing multiple gases has not yet been tested for feasibility. Next slide, please. So these are the customer requirements met by this subsystem, which I can explain in more detail on the next slide. So you can skip over this slide. So key features of this controller include a pressure transducer and thermistor probe by TE connectivity, which provides a digital pressure and temperature output of the tank. So given the volume of the pressure vessel and discrete pressure and temperature data, the quantity of each gas in moles and the molar flow rate from each tank can be captured digitally at any time. And so using this data, the motorized ball valve for oxygen gas and the solenoid valves used for the other gases can be programmed to dispense a quantity of gas based on the atmospheric parameters given by the user. So like the liquid handling subsystem, this design uses a peristaltic pump, which can be used for gases at low pressure. So once the gas from the tanks reaches the manifold, a pressure regulator will reduce pressure to then be pumped into each rubber capped test tube through the injection needle. This will allow the controller to inject precise amounts of gas autonomously, providing closed loop control of the culture conditions for each test tube. And this pump can be reversed in order to pump out effluent gases from each environment and can be used to pump out residual gases left over for transporting gas. And 2 servo-controlled stopcocks are used for redirecting pumped gas between the test tubes and the waste storage container. And to meet safety requirements, the pressure vessel has a factor of safety of 5 when containing inert gas at 800 psi. And all components are mounted to the outside of the frame, and all pneumatic threads are a 1/4 inch, meeting national pipe thread standards, allowing the design to be modular and easily assembled. Next slide.
So during the design process, the decision was made to divide heating and cooling into 2 different subsystems since they function independently from one another. For heating, the design resulted in the use of resistive heating elements attached to the wells and tubes to heat using conduction. The chosen heating elements consist of adhesive foils wired to an external temperature controller capable of heating up to 100 degrees Celsius. So as a result, some of the key features of this design are the adhesiveness of these foils, which makes installation very easy, as well as the use of the temperature controller, which allows for closed loop control and custom programming to allow us to create an autonomous system. Next slide. The TRL for the heating is level 6, since this is a component that is tested to full functionality by the supplier, but has not been tested within the constraints of our microbioreactor system. Next slide. And then lastly, for a quick overview of the customer needs that drove the design of the heating, I wanted to specifically highlight the modularity and ease of assembly, which is achieved through those adhesive pads, as well as the 100 degrees Celsius capability, which does exceed the customer need of 70 if desired. But lastly, we also don't foresee an onset of condensation during the heating process, since the heating pads have a pretty large surface area that can heat each tube very uniformly and at a controlled rate, thanks to the temperature controller. Next slide. So for the cooling system, the design process led to using a thermoelectric cooler, making use of the Peltier effect. Essentially, this transfers heat from the inside of the microbioreactor to the outside of the microbioreactor by flowing a DC current through the device. So basically it makes one side cooler and the other side hotter. And the specific cooler then transfers this heat difference using a heat sink and a fan assembly to transfer that to the air. So based on the dimensions of the incubator and the cooling requirement, the device identified has a sufficient cooling capacity of 26.25 watts, which is plenty to allow us to bring the temperature as low as -10 degrees Celsius for the specific dimensions of our incubator. And the system also brings a few key advantages in its very low number of parts, since I think the total number of parts is just 3. So there should also not be any discord with the heating system, since the heating occurs directly to the tubes via conduction, and that pretty much keeps the thermoelectric cooler isolated and prevents it from heating up beyond its maximum operating temperature. Next slide. And similar to the heating system, the cooling also has a TRL level of 6, since it's also a proven concept that just hasn't been applied and tested within the constraints of this specific system. Next slide. And then lastly, the needs that drove the cooling system's design are pretty similar to those of heating, but there's a few important capabilities that I wanted to point out, such as, again, cooling down to -10 degrees if desired, and keeping the maximum temperature, the external maximum temperature, below 55 degrees, since this is something that will be mounted or have a connection to the external side of the microbioreactor. And a quick point is that although the requirement asks that the durability is 10 years, the thermoelectric cooler itself does meet that requirement, but the fan itself is only rated for 4.5 years, but that's something that's pretty easy and very affordable to replace. Next slide.
The last subsystem we're discussing today is the user interface subsystem, which was designed with intuitiveness in mind. This explains why that there are only 4 main components on the main panel, the biggest being the Omron 3.5-inch touchscreen LCD display. Below this are 2 22mm push buttons that were envisioned to start and pause the machine. There's also an emergency stop button in the bottom right of the picture. All of these electrical components are encased in a 0.063-inch thick 6061 aluminum sheet casing. And this just makes sure that all the electrical components stay out of the enclosure of the incubator where the tests are being done. The TRL level chosen was level 3 to err on the side of caution, as touchscreens and buttons have been used in similar applications before, but we have not tested them specifically in our environments, so we rated it a 3. Next slide, please. This subsystem satisfies 8 customer needs. The first 2 we put our focus on were the need number 2 and need number 7, which involve giving the subsystem enough power to run and also being able to shut down the incubator in case of an emergency. These 2 needs were met by ensuring that the screen and the buttons met the 120 volt and 15 amp voltage and current specifications, and also including the emergency stop button from the previous slide. The rest of the needs can be combined as the customer requests an intuitive way to control and program the system's parameters while also communicating with the user the progress of the system during testing. And to satisfy all of these needs, the Omron interface screen with NB Designer software was chosen. Next slide. This screen, while being small and simple, has many other key features, including the ports on the back, which include an Ethernet port, which gives the screen internet access for it to come into contact with smartphones, as well as there are also 2 USB ports that are used for data collection and transferring code between the screen and the NB Designer software itself. The NB Designer software is a free HMI customization software from Omron that allows users to customize the display fully with switches, lights, graphs, timers, and animations. And these features also allow the user to have full flexibility in their testing by changing feedback between tests. Finally, the screen comes with 4 clamps on the corners of the pictures there to allow for easy mounting onto the aluminum panel. Next slide, please. Now, after completing all the subsystem concepts, we counted up all of our part totals for each subsystem to compare our part totals to some of the other teams during this class's symposium. As you can see from the chart here, we have a total of 399 parts, and after talking to a few of the teams at the symposium, we found that they had anywhere between 500 to over 1,000 parts. So we were pretty proud of the fact that we were able to fulfill our Hedgehog Concept goal of creating a system with a least number of parts, making it intuitive. Next slide. And also this part reduction had another impact on, which was our cost. So as you can see from this table here, the OTS and raw material costs come out only about a little over $6,000, and then adding in the manufacturing and assembly to that puts it a little under $8,000. Next slide.
So in sum, we designed this to be the most accessible, the cheapest, and the most intuitive bioreactor. Our concept uses components available to our department at UF, making it a perfect candidate for prototyping in 4502. The simplest solutions are often the best, and we believe that is exactly what we have here. And we're very confident that it will meet and exceed expectations. Next slide. To reiterate what we've said here today, we've created a relatively inexpensive modular bioreactor. Our design successfully meets the customer needs as well as our own team's goals, specifically simplicity of design. We'd like to thank this semester's sponsors from Northrop Grumman and Cummins, especially the representatives that could be here today. And we'd love to take any questions that you have from here on. Thank you for coming to our presentation.
All right, thanks guys for the presentation. Job well done. Do we have any questions from our panelists?
Hi, Dr. Traum. I have some questions if no one has any.
Yeah, they're ready.
Go ahead.
I had two questions for you guys. Overall, great presentation. Really enjoyed it. I had a question with the liquid dispensing department. You guys had the bottles on the side of the wall there. What was your reasoning in putting them there instead of maybe putting them outside?
A good point. I guess I didn't necessarily take that into consideration. I just assumed that the shortest possible route from the liquid handling and dispensing to the actual needle would be best.
Cool. And then I had one other question, and that was with your fluorescent system. You guys said you're using an array of LEDs and photodiodes. With the LEDs and such, is there a limitation to how many wavelengths you guys can examine with your system? Because it seems like if you're using like a breadboard, what's the ease of switching between the LEDs and such? Because I'm assuming you guys aren't using a filter cube or like a monochromator kind of thing?
Yes. I'm sorry, can you repeat the question?
So I was asking, is there a limitation to what wavelengths you guys can measure at a given time? Like if you wanted to measure like 2 different wavelengths, what would be also the ease of you switching out in case if you wanted to measure other wavelengths and such?
So if other wavelengths wanted to be measured, you could just replace the LEDs, but the intent was that you could only either measure optical density or fluorescent intensity at one given time.
Okay.
I think also I'd like to add that our design would allow you to, like, if you wanted to place 2, like say 2 LEDs and 2 sensors for each tube, so you could get multiple readings at the same time.
So would the user have access to the breadboard then? Would that be on the outside somewhere? Or would that be inside the container itself? I guess would be the last question I had.
It's inside the container, and they would have access to it, but it would take some like disassembling.
Okay, cool. Thanks, guys.
Thank you.
While we're here, we only have the capability of doing the OD and AFI measurements in these tubes that are sort of set between the breadboard. There's no capability of doing it in situ in the well plates?
Yes, that's correct with this design.
Okay. You'd mentioned that you've got fluid flowing in both directions through a common tube. Do you have any capability of sanitizing that tube? You've got if you want to take waste fluid out and then put new fluid in, you've got to pump a somewhat significant amount of fluid, right?
That would be easily done. You would have to kind of stop the process and remove the bottles, and you could replace it with like a sanitizing solution and then pump it through and then replace your culture medium and like hook that back up to the pump, but it wouldn't be like an automated process.
Okay. And when you're extracting fluid and dipping a tip of a syringe or whatever into multiple well plates, do you have a capability of sanitizing that between contact?
Sorry.
I
can.
You got it. You got it.
Yeah. In our current design, we don't have a solution, but we have envisioned that you might be able to add like a sanitizing station that your dispenser could like visit. Maybe it's like a liquid that it can dip into in between tubes, but we don't have that included at the moment.
Okay, and then one more, and I'm sorry, go ahead.
Real quick. As of right now, we have not fully fleshed out a solution for that, but we've discussed a little bit of it. I think that there's an assumption that the needle is going to go all the way into the fluid. It's just going to go through a little silicone nipple, and so the outside of the needle or the syringe wouldn't really be exposed to the sample, if that makes sense.
I think it does for dispensing, but not for withdrawing.
True.
One more, and then I'll kind of take a break. You said you've got 2 to 3 meter per second travel on your gantry system. That seems huge. What are the trade-offs that are involved in that, and why isn't it something more reasonable?
The 2 to 3 meter value was just listed as like a theoretical maximum of the system. What it would actually operate at is much, much lower because we don't need that kind of speed.
Sure. So why spec a system that's capable of it?
I guess it's unnecessary, but we didn't want to limit ourselves on the up like the top end. Yes.
Okay, not sure if we lost Tom there, if that was the end of the question.
That was the end of the question.
Okay.
So okay, so let me follow on here. On one of your earlier slides, you said you had the subsystem being 11 kgs, and then I know that you had subsystem specs. Was the entire weight 11 kgs, or just the subsystem was 11 kgs?
That was just the frame.
So how much is the whole thing? Like the full weight?
The full weight, less than 20 kgs total. Did not spec that out in SolidWorks, but I can get that answer for you. Probably not right now. That would be a later thing, but it's in SolidWorks. I just didn't note it.
I had a question.
Go ahead.
That's okay.
Yep.
Oh, yeah. Can we go back to the Omron display? And you had the visual there that showed how you could connect your high definition TV to the back of it, and your PlayStation or whatever else it was you wanted to connect to the back of that Omron thing.
This slide?
Okay, there we go. Yeah, so so correct me if I'm wrong, but when I look at the thickness of that unit and I imagine it installed in that aluminum sheet casing that you showed earlier, and then I think about how much depth you need when you plug in any kind of USB cable or Ethernet cable into those sockets at the back. You need about another inch, at least inch or two, to allow for the connector and the cable to bend beyond the back of this unit. And I don't think there's room for that in the aluminum housing that you've got there. I don't know, but I could be wrong.
Yeah, no, I think you might be right about that. I don't have the exact measurement of how deep it is. It's not like flush with the back, so I did leave some room. And there's also the back of this kind of like, I don't know how to really show it, but like the top of it kind of goes out farther than like the bottom of it. So there is a little more room there than I think it shows. Like that surface there, that bottom picture is not all flush. But I do think you're probably right in the fact that if there is a cord that has much of a bigger thickness, that's something that could be expanded. But I don't think that would have really too much of an effect on like the cost of it, just because the sheet metal is pretty cheap and it's pretty flexible.
Oh, it's easily fixed. I was just, it's just a kind of a basic design mistake. That's to put it meanly.
No, yeah, that's fine. Thank you.
Thanks.
I had some feedback too. So good job overall. I liked how you had your customer needs listed and how you addressed them throughout each subsystem. It was good to see that you guys kept those in mind and made sure that those are your goal to keep. So I like seeing that. Could you go back to and give me some more detail on the cooling aspect of it, the Peltier effect? Maybe that's new to me. I don't know how this works. Could you give me some more input on?
Absolutely. That's a great question. So the way the Peltier effect works, it's also often referred to as just the thermoelectric effect. It's essentially a conductive method where there's two plates within the cooler itself, one on each side with heat sinks on both sides. And you can essentially run a DC current through the device in either direction to either drive heat from one side to the other side or opposite. So in theory, the device can actually also heat, but we're specifically using it just for cooling because its heating capability isn't as high as the customer desired it to be. So that's why we added the additional heating system with the individual pads. But essentially the fan circulates the air through the heatsink, cooling it over time as the device is turned on and uses the effect.
Okay, interesting. And there was no, so it looks like you're buying this machine that is capable of doing much more, and it's just not, you're paying for more than you need, right? Was there no other options to have just the strict cooling capability?
To an extent, you're right with that. And there are alternative options that I suppose are specific just for cooling, but I found this to be extremely affordable. The device only costs, I believe, in the $200 to $300 range. And like I said, it was just a very simple to implement. So I think the cost benefit of the simplicity of this implementation outweighed any benefits of any alternative devices, which might have included, for example, liquid cooling was just a more complex solution that required more tubing and just more complexity overall.
At a minimum, I mean, it could reduce the number of the little sticky resistive heaters that you're needing to add in there. If you have some heating capability that's just not quite enough to get it done, you only need to supplement that. So that could reduce cost, reduce part count.
That's also a good point.
Yeah, could you go into also where you're placing these heating pads? I didn't really see, it just showed a picture of it, didn't show where they went.
So I actually think the best place to show where it would go is if you scroll back to the liquid storage system. The pad itself measures 1 by 3 inches. So it would literally just be adhesively stuck onto the tubes themselves above the region where so it wouldn't interact with the OD or FI measurement systems. If you can go to the tube and disk storage slide, Alex. That one, yeah. So it would be above where the OD and FI housing device is.
Okay.
And
and lastly,
stuck to the case of the I don't know what we're calling it, of the incubator.
Can you repeat that?
They're just stuck to the case of the incubator?
They're stuck to the tubes themselves.
Oh, to these tubes themselves. Okay, so they're directly heating the tubes.
Yeah. Which I don't see as an issue since glass, the melting temperature of glass is way, way higher.
Oh, sure.
So you could potentially control the temperature of each individual.
Yeah, and that is a capability given the temperature controller that was selected.
Okay, good. And lastly, just here, this is a good picture here. What pressure are these gas tanks holding?
Well, we didn't really get any sort of specific, but it's rated to withstand about 800 psi. So basically any range within then, and obviously the calculations sort of depend on that.
Okay, and I'm just looking at it from potentially just a safety aspect where maybe you want to provide some sort of shield or something in case that something goes and something's punctured. It just seems like just anytime you store high pressure gas anywhere, there's the risk of something going wrong. So
oh yeah, I mean it definitely depends on how the user operates it. I mean obviously they should not keep it anywhere hot.
Okay. Yep. Something to keep in mind. Good job, guys.
Well,
Thank you.
Well, those containers are right next to the thing, so it'll add weight. And if you're storing it at high pressure, it seems a little dangerous. I don't know. Maybe a little more separation, or what if you were to just offboard the gas tanks themselves, right? And just have a controller coming in and leave it up to the user itself. You would lose weight and you would lose everything else. Safety considerations, right?
That's definitely true.
It probably also makes it more convenient for a lab. I mean, the lab probably has all the gases on hand that they'd want to use, and they don't have to worry about, they have the special tank that fits on your unit. If it's connected to, whatever they've already got on hand, that's more convenient.
Yeah, I mean, it would definitely make the design a lot simpler if it came in a pre-mixture, but it was definitely a challenge trying to design a controller that could inject multiple gases into each tube.
I also want to add that that you guys are correct that this system, maybe not as it's built now, but could easily be kind of modified to just attach to like a standard gas tank that a laboratory might have.
Okay. Do we have any more questions from our panel?
What do you anticipate a user being able to do with the 2 buttons and an emergency stop on your control panel?
The main reasoning to add the the emergency stop was obviously just the entire system shutting down of just in case of an emergency. The other 2 buttons, I just wanted to add some extra programmability in terms of like having obvious buttons to like, I want to start it, I want to pause it, where there wouldn't be any like, because the screen is kind of small, any like slip of a hand or something of like you accidentally start something or accidentally pause something. I thought the screen would be better for more feedback and like changing of the parameters of the system, and the buttons being more of like a stop and a pause. But they also, those can be programmed in another way if the user would like. It just adds some extra flexibility.
Okay. Any other questions from our panel?
For your XY motion, the big rectangular bar that the supports are running across, are those precision ground surfaces, or are those just going to be like extrusions?
Which bar?
The one on the left hand side, and then the one that the middle one.
So those are like CAD mock-ups of the actual product. They're not bars. They're like a belt driven, like with guide rails kind of system. So I don't know if they're precision ground, but the
Is it an
product.
OTS part?
Yes, yes.
Oh, okay.
So yes, the product as it comes, it's made to, you know, run smoothly.
Okay. Yeah, so we started about 10 minutes late, and we're now, even with that 10-minute buffer, we're about 5 minutes over the time. This is the last group of the day. So if anybody has kind of one final wrap-up question, maybe we could have them field that and then call it an afternoon if anyone has anything.
Just commendations. Good job, guys.
Thank you.
There you go.
Appreciate
Good way
it.
to end things.
Thank you. Thank you.
Thank you very much for all of the feedback
good
and
job.
constructive criticism.
Thanks for inviting us.
All right, very good. Okay, so let me stop recording.